Today we're going to talk about the rational root theorem. The rational root theorem is the foundation for our next few lessons. So let's get right into it. The rational root theorem says that if you have a simplified polynomial with integer coefficients where your polynomial is equal to 0, it has a rational root in the form p over q. Now, the simplified polynomial does have to be in standard form. P represents all of the factors of the constant term of f of x, the last term when it's written in standard form, and Q represents all of the factors of the leading coefficient of f of x. We want to use the rational root theorem in order to find all possible rational zeros for the function. This polynomial is written in standard form, so let's identify a few things first. The constant term, our P, would be positive 2. The factors of 2 are 1 and 2, but also negative 1 and negative 2. So anytime we're listing factors, because of that combination of negatives and positives to get somewhere, we always want to write plus or minus in front of each of the factors. So there are actually 4 factors to 2. The leading coefficient of this is 1. There's a hidden 1 in front of here. Remember that. That's our Q. Again, it's positive 1, but because of that plus or minus, it really doesn't matter what we write there. We know that the factors of 1 are, 1. 1 times 1 is 1. There's no other way to get there unless you count negative 1 times negative 1. But we accounted for that in our plus or minus. So in order to write our list of factors, we want to start in the fraction form P over Q. Our P is going to come right from the factors I listed for positive 2. In the numerator. Our Q is coming from the factors I listed for positive 1 in the denominator. Our possible roots are all of those divisions. So plus or minus 1 divided by plus or minus 1 is plus or minus 1. 2 divided by 1 is 2. So we have 4 possible roots, positive 1, negative 1, positive 2, and negative 2. In our second example, we're going to look at how these possible rational roots, because how does knowing 4 of the possible roots here help us with this polynomial? Like I said, we're going somewhere with this. So let's see where that somewhere is for now. So if we start here with our possible roots, we identify our constant term as positive 10. This is going to lead to P. The factors of 10 are 1, 2, 5, and 10. Putting a plus or minus in front of each of those, creating our numerator. And in our denominator, we want the factors of 12. Those are going to lead to our Q's. Factors of 12 are 1, 2, 3, 4, 6, and 12. Remember, factors are what multiply to the number. So like 3 and 4 are factors because 3 times 4 is 12. 2 times 6 is 12. 1 times 12 is 12. Our list of actual possible zeros comes from dividing each of those. So first we're going to divide all of our numerator by 1, resulting in plus or minus 1, 2, 5, and 10. Then we go through and divide all of our roots by 2. So 1 divided by 2 is 1/2. 2 divided by 2 is 1, but I already have that written down, so I'm not going to write it again. 5 divided by 2 is 5/2. And again, 10 divided by 2 is 5. Already have it written down. Don't have to write it again. We're going to go through and divide those blue numbers by each of our denominators to get our full list. So here's our list of possible roots. Now, this is a list of 32 possible rational roots, which seems like a lot, but we are leading somewhere. This will help us, I promise. Think about what we've narrowed down from. When we talk about possible roots of the polynomial, before this list, you had infinite options, any real number, right? We've narrowed it down to 32. We've done some pretty good work here. We'll continue the conversation about finding roots in future lessons. But for now, let's apply this list a little bit. We know that we could find roots of the polynomial from the factored form of a polynomial. So if we are looking for a root of negative 1, we actually have to consider the factor x plus 1. If you set that equal to 0, solve for x, you get -1, right? We can get there. So we know that the factor x plus 1 is the root of the polynomial if we perform long division and we get 0 as a remainder. So let's do it. Is x plus 1 a factor? Perform your long division. We find out that no, it's not. It has a remainder of -1. So -1 can't be a root because x plus 1 is not a factor of the polynomial. But that process is long. So our question is there a better way to do that? Well, if you're checking for roots, there is, and that process is called synthetic division. So synthetic division essentially pulls all your information from your long division setup without the variable. When we set it up, we're going to be testing the root. I always say my root is in the box. So I put it off to the side. The number we're testing is -2/3. Our question is that a root of the polynomial? If it is, the remainder would be equal to 0. I pull my coefficients of the polynomial in question with placeholders. So if you were going to put a placeholder into it for your long division, you have to pull the coefficient of 0. My coefficients for this polynomial are 12, 23, and 10, all positive. I write those like this. This is our setup. The first step to synthetic division all the time is to bring down the first number. Our remainder is going to go in this last space. Whatever this number is becomes our remainder. We will practice synthetic division quite a bit in class, so don't worry if you don't get it the first time. We're going to perform our long division. We multiply. -2/3 times 12 is -24/3, which is -8. And then we add straight up and down. 23 plus -8 is 15. Then we multiply. -2/3 times 15 is -30/3, which is -10. Place that here. And we add straight down. 10 plus -10 is 0, which is great news, telling us that -2/3 would be a root of the polynomial. This is just an introduction to synthetic division. We will talk about this process more in class and in future lessons.